Hello students, welcome to the class on control engineering. So in this video we are going to solve about the Bode plots, problems related to Bode plots, stability analysis using Bode plots. So I have listed out step-by-step method how to solve this one. Okay, so let us take on the first problem. So the problem is being given like this: a unity feedback system has g of s is equal to 80 divided by s into s plus 2 into s plus 20. So draw the Bode plot, determine gm represents gain margin, pm represents phase margin, omega gc represents gain crossover frequency, and omega pc represents phase crossover frequency. So for this we have to draw the Bode plot. Okay, and we need to find out these terms. So what is the step number 1? So this is the step number 1. So usually they going to give the open loop transfer functions. This is the standard form of representing open loop transfer function. So this has been given in the problem. So we have to convert this standard form to time constant form. So let us see how to convert from standard form to time constant form. Okay, standard form is g of s into h of s is equal to 80 divided by s plus 2 s plus 20. What is the step number 1? We are going to convert this standard form to time constant form. That is the step number 1, converting to time constant form. So that is equal to, what is h of s here? So here h of s is not given. Instead of that, they are telling it is a unity feedback system. Unity means 1. Okay, g of s into h of s is equal to 80 divided by s. See, out of s plus 2, I am going to take 2 as common. I am going to write as s plus 2. Here I am going, s by 2, 1, right? Here I am going to take 20 as common. I can write this one as 1 plus s by 20, right? So this is how we are going to convert into given standard form to time constant form. So after simplifying it will be written as 2 divided by s 1 plus s by 2 into 1 plus s by 20. So this one we have converted from the standard form to time constant form. So this is the step number 1. Next, what is step number 2? Identify the various factors. So we have different factors are there. So I would like to first we need to identify the k. So in this problem, what is k? So k is equal to 20. So just comparing with the time constant form, and we are going to taking the various factors. So when we compare, so what is the value of k? That is step number 2. Identify the factors. K is equal to 2. Now the step in the second step, so next step is number of poles or zeros at the origin. Okay, so in this problem we don't have any zeros at the origin. We have one pole at the origin. See, s is equal to 0. That is the first root. So therefore the first term. Second term is number of poles or zeros at the origin. In this problem we have one pole at the origin. Okay, one pole at the origin. Third factor that we have to find it, number of simple poles or zeros and corresponding corner frequency we have to find out. Okay, so here we don't have any zeros, right? So we have one pole at the origin and we have two simple poles. So these we are going to call as simple poles. I am going to take this one simple pole. What is a simple pole? We have 1 by 1 plus s by 2. So this is a simple pole we have. So we need to find out the corner frequency for this simple pole. What is the corner frequency? Omega c is equal to 1 by t. Okay, omega c is equal to 1 by t. So here what is t? So from this t is equal to 1 by 2. You just compare this and this. Okay, so 1 plus sta. What is ta represent? Here 1 by 2, that is the t. So if I substitute it, so this will becomes 1 by 2, that is equal to 2 radians per second. Okay, this is one simple pole. So we have another simple pole, that is fourth factor, another simple pole. What is that simple pole? 1 by 1 s by 20. So this is another simple pole. So from this, what is the value of t? That is equal to 1 by 20. Therefore corner frequency is equal to 1 by 20, that is equal to 20 radians per second. See here, from this simple pole we have 2 radians per second. From this simple pole we have 1 by 20 radians per second. Which one is smaller? So 2 radians per second is the first corner frequency. That's why this is a omega c1. Next one is, this one is a omega c2. So these are the various factors. Okay, I hope you understood. So step number 3. What is step number 3? Step number 3, magnitude plot. We need to step number 3 itself is the drawing the magnitude plot. To draw the magnitude plots, we need various requirements. Let us go one by one. So what is the contribution of magnitude k? We have 4 factors are there. Out of these 4 factors, what are the various contribution to the magnitude plot? So that we are going to try to identify in the step number 3 to draw the magnitude plot. Step number 3, that is to draw magnitude plot. Okay, so what is the contribution of k? Okay, so step number, in this step number 3, first factor, that is k. So k is how much? K is equal to 2. What is the contribution of k to the magnitude plot? That we can find out. Magnitude, we are given magnitude is equal to 20 log 10 to the base 10k. Okay, so we are going to substitute k is equal to 2, and we are going to find out the factors. Okay, so 20 log 2 to the base 10. So this we got 6 dB, 6 decibels. Magnitude is equal to 6 dB. Now what to do with this? So we are going to draw a line parallel to 0 dB line. So magnitude, we are going to draw a line parallel to 0 dB line. If k is greater than 1, so we are going to draw the line above the 0 dB line. So this is the first factor. Okay, so let us see how to represent this k is equal to 2, that is the magnitude of 6 dB on the semi-logarithmic sheet. So this is a semi-logarithmic sheet. So now I would like to explain how to represent the various factors and all. See, so this is going to start the smallest value, that is 0.1. Okay, so it is going to start with a 0.1. Next, from year to year, so it is going to vary 0.1, 2, 3, 4, 5 like this, and it will end at 1 radians per second. So this is the x-axis. So that is a representation of omega frequency. So in the Bode plots, we are going to vary the value of omega from 0 to infinity. Okay, next 1. So after this 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10. After this it will be 20, 30, 40 like that. So this will be 100. Next it will be 1000. Next it will be 10,000. Okay, so this is 10,000. So from 0.1 to 1, so this range we are going to call as 1 decade. So this is 1 decade. From 1 to 10, that is also 1 decade. 10 to 100, this is 1 decade. 100 to 1000 is 1 decade. So this is how we are going to divide the semi-logarithmic sheet. Why it is called as semi-logarithmic sheet? X-axis it is a logarithmic, whereas y-axis is a linear scale. Okay. After representing the omega, so next we need to represent the magnitude plot. I am telling you how to draw the magnitude plot. I am going to consider this as a 0 dB. So from here to here, so this is 1 unit, that is 1 centimeter, or 1 box I am taking it as 20 dB. So it is been divided into 5 units. Okay, 20. Next this one is 40 dB, this one is 60 dB. In the same way, below this it will be minus 20 dB, minus 40 dB, like this. Okay, so now first I am going to represent the various factors we found out. The first factor that we found out now is K is equal to, what is the magnitude? That is 6 dB. How to represent this? First I am going to draw the 0 dB line like this. I will use the sketch pencil so that it can be easily identified, but everyone can use the pencils for this. I am going to draw the line for 0 dB. So this is a 0 dB line. Okay. Next, I need to represent the corner frequencies. What is omega C1 is equal to 2 radians per second. Omega C1. So where is this is 1 and this will be 2. So this is the omega C1 is equal to 2 radians per second. So I am going to draw a line from 2 radians per second upwards. Right? So this is the omega C1. Next, what is omega C2? That is equal to 20 radians per second. I am going to represent, this is a 10 and this one is 20. I am going to draw upwards. This is a omega C2, 20 radians per second. So after this, just now we found out that magnitude K is equal to 6 dB. How to represent this? So here is a 0. So each unit represents 4 dB. So 4, this one is 8. In between this 4 and 8, I am going to mark 6 dB. Right? So this is a 6 dB line. I am going to draw a line parallel to 0 dB line above this. Why it is above? As per the rules, see here, if K is greater than 1, I am going to draw a line above the 0 dB line. If K is less than 1, I am going to draw below the 0 dB line. So this is the step number 1 in the step number 3. Okay. Now I am going to draw the line from this. So this is a contribution of K, that is a magnitude, that is equal to how much? 20 log K, that is 2 to the base 10 is equal to how much? 6 dB. So this is how I am going to represent the 6 dB. Okay. So next, another reference lines I want. So that is I am going to draw a reference line from 1. So this is 1. And where it intersects with the 0 dB. So this reference line is want. Why we want is, so from this we need a slopes, right? So from this 1 radians, I am going to draw the reference lines. So this is the line from this 0 dB to 20 dB. This point and from this point. These are the reference line. So what is this represents? So this represents the slope of minus 20. This represents the slope of minus 40. This represents the slope of minus 60. Okay. So this is minus 20, minus 40. This is a minus slope of minus 60 dB. In the same way, if I draw it from here to here, sorry. So this is slope of what? Plus 20 dB. So this is a slope of plus 40. It is moving upwards, right? Slope is moving upwards, then it is plus. If it is moving downwards, then it will be a negative. So this is the basic thing we need to prepare before drawing anything. So I need to mark omega C1, omega C2 and this reference slope. So these are the slopes that I need to draw the magnitude plot. Then I have represented the K, that is 20 log 2 to the base 10, that is equal to 60 dB. So this is the initial preparation that we have to make for the magnitude plot. Okay, what next? See, I have next factor, that is one pole at the origin. So sorry, I need to write the conclusion for this, right? After finding 6 dB, so what I did, draw a line parallel to 0 dB. So here we are going to draw a line parallel to 0 dB above and above. Okay, at 6 dB. Okay, we are going to draw a line parallel to 0 dB above at 6 dB. So this is the step number 1. Next, what is the step number 2 in the magnitude plot is poles at the origin. So what is that? We have one pole at the origin, right? So we have one pole at the origin. What is the contribution of this one pole at the origin? So one pole at the origin contributes minus 20 dB per decade. If we have n poles at the origin, then it will be minus n into 20 dB per decade. So in this case, we have one pole at the origin. Therefore, step number 2, one pole at the origin contributes how much? Contributes minus 20 dB per decade. So it is going to contribute minus 20 dB per decade. If we have 1 0 at the origin, it contributes how much? Plus 20 dB per decade. But here it is going to contribute how much? Minus 20 dB per decade, because we have pole, not the 0. Okay. So now what to do? So we have minus 20 dB per decade. That is a contribution of one pole at the origin. So we are going to draw. What we are going to do? We are going to draw a line parallel to draw a line parallel to minus 20 dB, parallel to slope of minus 20 dB until omega C1, that is 2 radians per second. So we are going to draw a line parallel to minus 20 dB until omega C1 2 radians per second. How to do it? So let me show you. Right. So this is the sketch what we have. So this is a reference point from 1 radians. So I am going to draw a line first above this until it touches the 6 dB line. So this is 6 dB line. I have drawn a vertical line from this 1 radians per second to this magnitude of how much? 20 log, that is 6 dB. I have drawn a vertical line like this. From this point, I am going to draw a line parallel to slope of how much? Minus 20 dB per decade. Okay. And I am going to extend the same until it touches the corner frequency 1. Did you find it? So from this 1 radians per second, I have drawn a vertical line upwards until it touches the 6 dB line. From this point, I have drawn a line parallel to minus 20 dB. Why? Because we have one slope at the origin. What is the contribution of one slope at the origin? It is minus 20 dB. So this represents contribution of K and as well as one pole at the origin. So it is a slope of how much? Minus 20 dB per decade. So that is a contribution. What is the next contribution? So at omega C1 is equal to 2 radians per second, we come across one simple pole. Okay. So what is the contribution of one simple pole? Simple pole contributes minus 20 dB per decade. Okay. How to represent this? Simple pole. Third step. At omega C1, that is 2 radians per second, we have one simple pole, right? What is a simple pole? That is equal to 1 by 1 by s plus 2. What is the contribution of one simple pole? So it contributes minus 20 dB. Okay. So from the simple pole, it is going to contribute minus 20 dB. Whereas resultant slope, what is the resultant slope? Resultant slope is equal to, what is the previous slope? So from this we have previous slope is minus 20. From the one simple pole, it is going to contribute minus 20 dB. So we are going to get minus 40 dB per decade. So now what we are going to do? We have to draw a slope of how much? Minus 40 dB until corner frequency 2. What is 2? Omega C2 is equal to 20 radians per second. Okay. So how to represent this one? See, from this point, so I am going to draw a line which is parallel to minus 40. Okay, I am going to take like this and I am going to move it upwards. Be careful in this. Okay, from here I am going to draw a line until it touches the corner frequency 2. So this is slope of how much? Minus 40. So what is the contribution? This line, this slope we got due to the contribution of K 1 by S and one simple pole 1 divided by 1 plus S by 2. So what is the contribution? Minus 40 dB. Okay, this is slope of minus 40 dB. So here it is coming across the corner frequency omega C2 is equal to 20. So this omega C2 is due to the another simple pole. Okay. So fourth factor, at omega C2 that is equal to 20 radians per second, we come across another simple pole, right? Another simple pole 1 by 1 plus S by 20. So it contributes how much? It contributes minus 20 dB per decade. So therefore resultant slope is equal to, what is the slope? Previous slope, it is minus 40. What is the contribution of this? It is a minus 20. So therefore this will be equal to minus 60 dB. Okay, how to represent this? So from this point I am going to draw a line which is parallel to which one? 60, slope of 60, like this, and I am going to move. So I am going to draw a line parallel to 60. Okay, so this is the final slope. Okay, so this is due to the contribution of K and 1 by S and a simple pole 1 plus S by 2, and also due to 1 by S plus S by 20. So this is a final slope. What is the final slope? That is minus 60 dB per decade. Okay, so this is how we are going to draw the magnitude plot. Okay, so after drawing the magnitude plot, the next step is to find out the how to draw the phase angle plot. So let me show you how to draw the phase angle plot. What are the steps associated with it? Okay, so if you have quadratic factors and all, it will come in the next problem. So let us see. Okay, so step number 4 I have here. So step number 4 is to draw the phase angle plot. For this we are going to prepare a table. Okay, what is the table? See, I am going to prepare a table. Step number 4, phase angle plot. So we are going to prepare a table. So in this table, actually we are going to vary the value of omega. So therefore I am going to take the first component is omega, that is equal to in radians per second. Omega will be in terms of radians per second. That is the first thing what we are going to do. So here we are having various factors. What are the various factors we have? The first factor, we found out how many factors? There are 4 factors are there in this problem. Which are the 4 factors? So K is equal to 2, 1 pole at the origin, 1 simple pole and another simple pole. So these are the 4 factors are there. Therefore, what is the contribution of K to the phase angle plot? That is a K. That is the first one. Next factor that we found out is the 1 simple pole. That is 1 simple pole. What is the contribution of 1 simple pole? So next we have 1 pole at the origin. Next we have 1 simple pole. What is the 1 simple pole? 1 by S by 2. This is a 1 simple pole. Next we have another simple pole, that is 1 plus S by 20. This is another simple pole. Next is the resultant. So we need to prepare a chart like this. What is the contribution of these to the phase angle plot? Okay, see, if K is greater than 0, it is going to contribute how much? 0 degree. If K is less than 0, then it is going to contribute minus 180 degree. So in this case, so what is the value of K? So K is equal to 2. So therefore it is going to contribute how much? 0 degree. If K is greater than 0, contribute 0 degree. For all values of omega, K is going to contribute 0 degree. Next one is we have 1 by S, right? So we have 1 by S. I will take this another sketch pen. 1 by S. So this 1 pole at the origin contribute how much? Minus 90 degree. So one pole at the origin is going to contribute how much? Minus 90 degree. If it have a 0, then it is going to contribute plus 90 degree. So here we have pole, it is going to contribute minus 90 degree. Next we have simple poles, right? So first simple pole that we have 1 by 1 plus s by 2. So this is a one simple pole. So what is the contribution of this? See, so it is going to contribute minus tan inverse t omega, or we can take tan inverse of y by x. This it is a complex number, right? So we can find out the angle, phase angle tan inverse of t omega. So that means we are going to write I omega instead of s. Okay, so in this case we have 1 plus s by 2. What is the contribution of this? This will be equal to minus tan inverse of omega by 2. That is the t values. Instead of s we are going to write I omega. So that will be omega by 2. In the same way, see, minus tan inverse of t omega. What is t here? 1 by 2. Omega will be there. Next one is we have another simple pole, 1 by 1 plus s by 20. So this will be minus tan inverse of what? Omega by 20. So this is a contribution to the phase angle plot. Okay, so what actually we are going to do in the phase angle plot? We are going to vary the values of omega, and we are going to find out the contribution of this. So here we are going to vary the value of omega by 0.2 with a small value. Why is with a 0.2? We have to take values of omega in such a way that at each decade we are going to have some points. So in between 0.1 and 1, at least we are going to take 2 to 3 values of omega. In the same way, in each decade we are going to take the values. Omega is equal to 0.2, 2, 8, 10, 20, 40 and infinity. Okay, so we are going to vary the values of omega like this. Okay, so at 0.2, when omega is equal to 0.2, we know the contribution of k, it will be always equal to 0. Okay, because k is greater than 0. Then what is the contribution of simple pole? It is minus 90. When omega is equal to 0.2, so here I am going to apply 0.2, so I am going to get minus 5.7. In the same way I am going to apply 0.2 here. I got minus 0.57. So therefore the resultant will be addition of all this. I am going to get minus 96.27. In the same way, so when it is 2, what is the contribution of k? It is 0. Simple pole minus 90. This is minus 44.5. Then it is minus 5.7. So then I got minus 140.7 degree. So this one I already, table is ready, so that's why I am writing it down. You can do it with the help of calci. At 8, so it will be 0. This is the minus 90. So this will be minus 75.96. Then this will be minus 21.8, and this is the resultant slope 187.76 when omega is equal to 8. In the same way, for when omega is equal to 10, so 0, minus 90, minus 78.69. Next it is minus 26.56. Resultant is minus 195.29. So for the slope of 20, when omega is equal to 20, so 0, minus 90, this will be minus 84.28, minus 45 degree, minus 219.28. When omega is equal to 40, so this is equal to 0, minus 90, minus 87.13, minus 63.43. This we got minus 240.58. When it is infinity, so this will be 0, minus 90, minus 90, minus 90, and this equal to minus 270 degrees. So this is how first we are going to prepare the table. That means what are the contributions of various factors to the phase angle plot. I hope you understood. As I told, Bode plot consists of magnitude plot as well as phase angle plot. So magnitude plot is already over. So now we need to prepare for the phase angle plot. So therefore here the reference line one was 0 dB. Here I am going to take a reference line at any convenient point. I am going to take this as a reference line, and here it will be starts with minus 80. So this is the main reference. So above this I am going to mark this as a minus 150. Then it will be okay. This will be minus 120. This will be minus 90. Below this it will be minus 210. Next minus 240. Then minus 280 like this. Okay, so I am going to take the reference line like this. So it will start with minus 180. Now for each values of omega I am going to mark the corresponding point. So from the previous step, what is for 0.2, what is the resultant? Minus 96.27. Okay, for 0.2, so 0.2, so minus 96.2. So somewhere here I am going to mark. Okay, so in the same way, when it is 2 radians per second, it is minus 140. Okay, so here we have 150 for 0.1 is right, 2 radians per second. So 2 radians per second. So we got, how much is this? Minus 140. So here it is 150, somewhere here I'm going to mark. Okay, so next when it is 8, so it is minus 187. Okay, 187. When it is how much? Sorry, 8, right? 8. Set 2, 3, 4, 5, 6, 7. Sorry. 8. This is 8 radians per second. So how much is this? 186, somewhere here. Okay. Next, when it is 10, it is minus 195. Minus when it is 10, it is minus 195. So somewhere here. When it is 20 over 40, it is minus 240. 240. When it is right 40, right? So it's 20, 30, 40 like this. We are going to mark minus 240. Right. So this is how we are going to mark the phase angle plot. And then I am going to connect with a smooth curve. So this is a smooth curve I am going to connect. So I am going to draw the sketch pen so that it will be visible for you. Okay. See, we need to draw this with a smooth curve in such a way that at least it should cross this minus 180 degree. Okay, so this is how we are going to draw the phase angle plot after the preparation of this chart. Okay, so now magnitude plot is over, phase angle plot is over. What are the things we have to find out? We need to find out first omega gc and omega pc. What is the meaning of gain crossover frequency? How to find out gain crossover frequency? See, that we can find out with the help of magnitude plot, where actually it crosses the this is a magnitude plot where actually it crosses the 0 dB line. So this is where it is going to crossing the 0 dB line. With the help of scale, I am going to draw a line downwards, vertical line downwards. So this is the point where this magnitude plot is crossing the 0 dB line. So this is what we are going to call as omega gc. Omega gc. How much is this omega gc? Approximately I am getting as 2.1 radians per second. Okay, so what is omega gc? Gain crossover frequency. That means where the magnitude plot crosses the 0 dB line. So that is the omega gc. Next, what is omega pc? Phase crossover frequency. That means where this phase angle plot crosses minus 180 degree. So that we are going to consider as phase crossover frequency. So this is the where it is going to cross the minus 180 degree line. So this is a phase crossover frequency. So approximately this 2, 3, 4, 5, 6. So I got omega. So this is the omega pc. What is omega pc? That is equal to 6 radians per second. Okay, approximately it is 6 radians per second. Now omega gc is over and omega pc is over. So next is to find out the phase margin. What is the meaning of phase margin means? See, for that we need to consider the omega gc. So this is the omega gc. See, it is, I have drawn a line, vertical line from the omega gc. So it intersects the phase angle at A and the reference line at B. Okay, so this is a phase margin. Okay, this represents the phase margin. So this is a phase margin. I hope you got it. Phase margin from A to B. So what is that? So here each unit, 1 second. Okay, so phase margin for each box represents 6 degrees, right? So it will be 6. So I have across 1, 2, 3, 4, 5. So phase margin approximately is equal to 30 degree. Okay, see, if it is above this minus 180, if you are marking this as a above, so then it will be positive. Phase margin is positive. Next one, we have to find out the gain margin. How to find out the gain margin? So for that we need to consider omega pc. Pc, that is 6 radians per second. From this point I have drawn a vertical line upwards. So here it is intersecting this magnitude plot at C and this reference at D. So what is the distance from this to this? Here 1, 2, 3, 4, approximately 4 units. Each unit represents 4 dB, 16 dB plus 16 dB. See, so from the reference line, if I am measuring it from downwards, then it will be plus. Okay, if it is above, it will be minus. Here gain margin is 16 dB, whereas the phase margin is equal to 30 degree. So this is the data that we got from this. Okay, so we got the various values. What are the various values we got? Omega GC, that is the gain crossover frequency, that is how much? 2.1 radians per second. Next, omega PC, that we got is 6 radians per second. Next one, phase margin we got is equal to 30 degree. Then gain margin, that is GM, that is equal to 16 dB. So these are the various values that we got. Now what next? We need to tell what is the stability of this. There are different conditions are there. So stability conditions: when omega GC is less than omega PC, GM and PM are positive, then the system is stable. So this is the first condition. Second condition, when omega GC is greater than omega PC, GM and PM will be negative, then it is an unstable region. Then omega GC is equal to omega PC, GM and PM are 0, then it is marginally stable. So in this condition, so we are satisfying the first one, that is omega GC is less than omega PC. See, omega GC is less than omega PC, right? So what is the comment? So we have to write omega GC is less than omega PC, and we got PM and GM is positive, hence the system is stable. So this is the comment that you have to write at the end of the problem. I hope you understood. Thank you. Namaste.